I will talk about Markov processes. Markov processes, as the name implies, this is due to Markov. Andrei Markov is a famous Russian mathematician. We already know about Markov inequality, and he has lot of contributions in diverse areas of mathematics. Also, you note that Markov was the disciple, student of Chebyshev. Chebyshev also we know, Chebyshev inequality, Chebyshev polynomial, and he had two great students. One is Markov and the other one is Lyapunov. Him also we know in different areas of mathematics, for example control systems, nonlinear control systems, and of course probability different, like central limit theorem is associated with Lyapunov, like that. And Markov process has lot of applications. Application areas are also diverse. We will discuss about this. Now if we recall the concepts like law of large numbers and central limit theorem or large deviation theory, we discussed there a sequence of random variables which are independent. That is the crucial assumption, independent. Now Markov processes consider the evolution of the steady state behavior of a stochastic process with simple dependence model. So we are now digressing from independence. We are considering dependent random variables, sequence of dependent random variables, but that dependence is very simple. That is dependence, suppose current value will depend only on the immediately past value. So that way we can consider that a system with limited or with minimum memory, memory of immediate past. Markov processes are widely used in diverse applications like population studies, queuing systems, and the restoration of a degraded photograph. These are some simple application I am telling, but application areas are really diverse. Before going to Markov processes, we will introduce what is known as conditional independence. Markov model is built around the notion of conditional independence. Now we know when three events are independent. Suppose A, B, C are independent. A, B, C independent. What does it implies? Probability of A intersection B intersection C is equal to probability of A into probability of B into probability of C. So this is the definition of independence. Now we want to introduce the notion of conditional independence. We are considering three events A, B and C. The joint probability of A, B and C is given by this probability of, because we can start with this probability. So probability of A intersection B intersection C is equal to probability of A multiplied by probability of B intersection C given A. Now if we apply this chain rule, then probability of A intersection B intersection C will be probability of A into probability of B given A into probability of C given A intersection B. So that way we consider the joint probability of dependent events. But in the case of conditional independence, what we get is that is the probability of B intersection C given A is equal to probability of B given A into probability of C given A. Suppose given A is known. So given A, the events B and C are called conditionally independent if probability of B intersection C given A. Now given A, the probability of B intersection C. Now this this is conditional independent. So B and C will be conditional independent given A if the probability, this conditional probability is product of probability of B given A into probability of C given A. So B and C are conditionally independent. Given A, B and C are conditionally independent. And equivalently we can also derive, we can show that probability of C given A intersection B, because A is given, so that will be probability of C given A. So given A, C is independent of B. So that way we can define conditional independence. Thus, if B and C are conditionally independent given A, then the joint probability is given by probability of A intersection B intersection C will be probability of A into probability of B given A into probability of C given A. So this term ordinarily it would have been probability of C given A intersection B, but since C and B are independent given A, therefore we will get this probability is equal to probability of C given A. So that way we have introduced the notion of conditional independence, and this notion is applied in defining the Markov process. So we defined conditional independence, which is different from unconditional independence. Now we will apply this notion to Markov process. Now a random process, we are considering a random process xt. T belongs to some parametric set tau. So usually this T is time. So we are considering a process which random process which varies with time, and it is defined on some probability space SFP. So we have a random process. Now it is called Markov process if for any sequence of time, because this T parameter is time, and we are considering a sequence, increasing sequence of time. T1 is less than T2 is less than T3, like that. It is less than Tn, less than Tn plus 1. Suppose we are considering a sequence of time instance. So for this sequence of time instances, we want to study the probability. So suppose we define the CDF, probability that x of Tn plus 1 is less than equal to x. Now given the value of the random process at an instance of time, that is xt1 is equal to x1, xt2 is equal to x2, like that xtn is equal to xn. Suppose these are the values given for the random process, then what is the probability that x of Tn plus 1 is less than equal to x. So we have suppose this is the time axis, this is T0, T1, like that. So maybe somewhere here T2, here Tn, and then T of n plus 1. So these time instances are given. Now we are interested to find out what is the probability that xtn plus 1 is less than equal to small x, given that xt0 is equal to, suppose x0, xt1 is equal to x1, like that, xtn is equal to xn. So this probability, this conditional probability, if it is equal to that conditional probability of xtn plus 1 given less than conditional probability of xtn plus 1 less than equal to x given xtn is equal to xn. We do not bother about the values before tn. So earlier values we do not consider, only it is dependent on xtn what value it is taking. So therefore this probability, if this conditional probability is equal to probability of xtn less than equal to small x given that xtn is equal to xn, then the process will be called Markov process. So given all the previous value, this process depend only on the values at immediate past. So probability that x of Tn plus 1 is less than equal to some value x, given that all these values are given, suppose xt0 is x0, xt1 is equal to x1, etc. But this will depend only this probability is same as probability that xtn plus 1 less than equal to small x given that xtn is equal to xn. So then this process will be called Markov process. So we define the Markov process, general Markov process given xtn, the random variable xtn plus 1 is independent of xt1, xt2 up to xtn minus 1. So it is conditionally independent because given xtn, then only xtn plus 1 will be independent of this. This property is known as the Markovian property. So given the all past values, the probability will depend only on the immediate past. This is the Markovian property. We will discuss about Markov chain. We have already defined Markov process. Now the process xt takes values from a suppose set V. Then this set V is called the state space. So we will define the term state space, and that is the space V. So xt will takes values from this set V, and elements of V are called states. So V will have the elements which are called states. So that way, along with a Markov process, we have a state space V whose elements are called states. Suppose V is countable. We are considering a countable state space. Since V has one-to-one correspondence with some subset of Z, that is the set of integers, we can assume V as a set consisting of integers. Thus xtn is equal to I. What does it mean? It means that xtn takes the ith state. For such a process, the Markovian property can be expressed in terms of the probability mass function. So earlier we defined the Markovian property in terms of probability distribution function, but now if state space is finite or countable, we can express it in terms of the probability mass function, and the process is called a Markov chain. So we have defined now a Markov chain. Markov chain is a Markov process whose state space is countable. A Markov chain may be a continuous time Markov chain that we call it CTMC, or a discrete time Markov chain DTMC. So we have defined Markov chain which has state space B countable. Now out of the Markov chains can be divided into continuous time Markov chain and discrete time Markov chain. When time is continuous, then it is continuous time Markov chain. When it is time is discrete, then discrete time Markov chain. We will elaborate CTMC, continuous time Markov chain. Xt takes values from a discrete state space V, suppose, because we have considered this one-to-one correspondence. Therefore, suppose V is equal to 0, 1, 2, etc. Then xt is called a CTMC if for any n greater than equal to 1. Now you consider some n plus 1 time instances, t1, t2 up to tn plus 1. Now if probability of xtn plus 1 is equal to j, we are considering the conditional probability that xtn plus 1 is equal to j. Given suppose xt0 is equal to I0, xt1 is equal to I1, etc., xtn is equal to I. Now this conditional probability is same as probability of xtn plus 1 is equal to j, given that xtn is equal to I. So this is the continuous time Markov chain. Here we consider any instances of time. Suppose here we are considering n plus 1 instances of time. Now the conditional probability of xtn plus 1, that it takes value j, given that xt0 is equal to I0 xt1 is equal to I1, like that xtn is equal to I. Now this conditional probability will only depend on xtn is equal to I, that is equal to probability that xtn plus 1 is equal to j given xtn is equal to I. Then this process will be called continuous time Markov chain. So for any n you consider the conditional probability of the suppose current event that it takes value j dependent on suppose all past values known, then this probability will depend only on the immediate past value, that is xtn is equal to I. Then this process will be called CTMC, continuous time Markov chain. I will give an example. Suppose we know what is an independent increment process. Increments are independent. Suppose for any n greater than 1, we are considering t0, t1, etc., tn plus 1. Then probability that x of tn plus 1 is equal to j. We want to show that independent increment process is Markov. So how we will say, suppose xtn plus 1 is equal to j given that xt0 is equal to I0, xt1 is equal to I1, like that xtn is equal to I. This probability we are interested to find. Now if xtn is equal to I, then this xtn plus 1 is equal to j is same as that the increment is j minus 1. So this probability we can write like probability that x of tn plus 1 minus xtn is equal to j minus 1 given that xt0 is equal to I0, xt1 is equal to I1 up to xtn is equal to I. Now we can apply the independent increment property. This increment is independent of the past value. Increments are independent. So that way we can write this simply equal to probability of xtn plus 1 minus xtn is equal to j minus I. So this is, we have used the independent increment property. Now let us see what happened to this probability of xtn plus 1 is equal to j given that xtn is equal to I. So suppose this is tn and this is tn plus 1. So now that xtn plus 1 is equal to j given that xtn is equal to I, therefore the increment is j minus I, x of tn minus 1. So x of tn minus 1 minus xtn is equal to j minus I given that xtn is equal to I. Now this interval up to tn, xtn, suppose at this point tn, and this interval x of tn plus 1 minus xtn, they are non-overlapping, therefore independent increments are independent. So we can consider the independent increment property. So we have considered tn and tn plus 1. Now given that increments are independent, therefore probability of xtn plus 1 minus xtn is equal to j minus 1 given xtn is equal to I will be same as probability that x of tn plus 1 minus xtn is equal to j minus I using the independent increment property. Therefore what we have seen that probability of xtn plus equal to j given all these, that is equal to probability of xtn plus 1 minus xtn equal to j minus 1. This probability is same as probability that xtn plus 1 minus xtn is equal to j minus I. Similarly, probability of xtn plus 1 equal to j given that xtn is equal to I, this probability is also equal to probability that the increment is equal to j minus I. So for both case we got that probability is equal to probability of xtn plus 1 minus xtn, probability of the increment is equal to j minus I. Therefore probability that x of tn plus 1 is equal to j given all past values up to xtn is equal to I is equal to probability of xtn plus equal to j given only xtn is equal to I. So that way this process, that is independent increment process, is a continuous time Markov chain. Now next we will cover DTMC, discrete time Markov chain. Now we are considering a discrete time random process, that is xn. It is a sequence of random variables only, xn, n greater than equal to 0. So that way every instant n is equal to 0, 1, etc. This sequence of random variables is defined. Now suppose further, so that way it is a discrete random process and V is also discrete. From a countable set V, xn takes values. Then xn is called a discrete time Markov chain if now it will be a conditional probability mass function, probability that xn plus 1 equal to j, given that x0 is equal to I0, x1 is equal to I1, etc. up to xn is equal to I, is equal to this probability, this conditional probability is same as probability that x of n plus 1 equal to j, given that xn is equal to I. So it is dependent only on what is happening at the most recent past. So that way we have defined the discrete time Markov chain. Here that state space is also discrete and the time of the random process is also discrete. We can give a very simple example, trivial example. Suppose xn is a sequence of IID integer valued random variables. So we are this is a discrete time and it values also integer value it takes. So that way it is a state space is also countable. And then probability of xn is equal to j, given that x0 is equal to I0, x1 is equal to I1 up to xn is equal to I. This probability is now because of independence, that is probability of xn plus 1 is equal to j. And this is same as if I consider probability of xn plus 1 equal to j, given that xn is equal to I, because of independence this will be also equal to probability of xn plus 1 is equal to j. Therefore what we can say that a sequence of independent random variables, if I consider taking discrete values, countable values, is a Markov chain. It is a trivial Markov chain. So therefore a sequence of integer valued IID random variables is trivially a discrete time Markov chain. So that way we covered Markov processes, that is definitions of Markov processes, continuous time, Markov chain, discrete time Markov chains. So let us summarize what we learned today. So to summarize, we discussed about conditional independence. What does it mean? Probability of B intersection C given A, if it happens to be P of B given A into P of C given A, then we say that given A, B and C are conditionally independent. Given A, B and C are conditionally independent. So this is the concept we introduced. So given A, B and C are called conditionally independent if this relationship is true. Probability of B intersection C given A is equal to probability of B given A into probability of C given A. And using this conditional independence property, we showed that we can find out the probability of a joint event like probability of A intersection B intersection C is equal to probability of A into probability of B given A into probability of C given A. So that way if given A, if B and C are conditionally independent, we can find out joint probability using this relationship. Now coming to Markov process, we showed that for a Markov process, general Markov process, the CDF, conditional CDF, this one is conditional CDF, conditional CDF, cumulative distribution function. So this conditional CDF, given that xt1 is equal to x1, xt2 is equal to x2 up to xtn is equal to xn, is same as the conditional CDF given that xtn is equal to xn. Then this process will be called Markov process. And we also told that xt takes values from a state space V whose elements are called states. So we introduced the concept of states and state space. What else we considered? We discussed about continuous time Markov chain. For a continuous time Markov chain, now if we consider any instances of time, suppose x, probability that x of t n plus 1 is equal to j, given that xt0 is equal to I0, xt1 is equal to I1 up to xtn is equal to I, is same as probability that xtn plus 1 is equal to j, given that xtn is equal to j. So that way we define the continuous time Markov chain, where the Markovian property is defined in terms of probability mass function. So the conditional probability mass function given all these past values is same as the conditional probability mass function of xtn plus 1 is equal to j, given that xtn is equal to I. So that way we define the continuous time Markov chain, and we give an example, that is independent increment process is a continuous time Markov chain. Then we define the discrete time Markov chain, where both time and state space are discrete. So for a discrete time Markov chain, xn n greater than equal to 0, taking values from a countable set V, this probability that xn plus 1 is equal to j, given that x0 is equal to I0, x1 is equal to I1 up to xn is equal to I, is same as probability that xn plus 1 equal to j, given that xn is equal to I. We give an example, that sequence of independent random variables taking integer values, that sequence is a trivial Markov chain. So that way we introduce the concept of Markov chains. Now we will specifically discuss about Markov chain in the next class. Thank you.